viewers, in my last interaction with you, I had discussed keto-enol tautomerism in great details with you. And we know those carbonyl compounds which have alpha acetic hydrogen in them, they exhibit keto-enol tautomerism. Now the question arises, will formaldehyde, benzaldehyde, benzophenone or chloral exhibit tautomerism? Then the question is definitely no. These molecules do not have hydrogen in them. That is alpha hydrogen in them. So therefore, the question of acidic alpha hydrogen does not arise. So if a question is asked whether any of the above compounds which I have discussed with you will show tautomerism, then the answer is a definite no. On the other hand, if they ask which of the following will show keto-enol tautomerism, and the examples asked are benzaldehyde, formaldehyde, phenol, none of the above, then your answer is going to be phenol, because phenol is the enolic form of phenol. That is, this form is the aromatic form, whereas the keto form of phenol is an alicyclic carbonyl compound which is non-aromatic, and we know aromatic compounds are more stable. Therefore, phenol exclusively exists in the phenolic form, that is in the enolic form. I would like to discuss another interesting example with you today, that is of ethyl acetoacetate, which shows keto-enol tautomerism. This is a classical and most thoroughly studied example of keto-enol tautomerism. As you can see on your screens, you can see a molecule of ethyl acetoacetate which is existing in dynamic form, in dynamic mixture in solution of keto form and the enol form. The left-hand structure is the keto form, in which the methylene group is sandwiched between two electron withdrawing groups, which are the acetyl group and the ester group. Since this methylene group is sandwiched between two electron withdrawing groups, the hydrogens attached to this carbon are acidic in nature. Let me again point out here that the alpha carbon here is the carbon of the methylene group. This carbon is next to the functional group, that is the ester group. So it is alpha to the carbonyl group of the ester, and at the same time it is also alpha to the carbonyl group. So this clearly indicates the hydrogens of this methylene group are going to be acidic in nature, since they are sandwiched between two electron withdrawing groups. As a result of which, the bond between the alpha carbon and the alpha hydrogen will weaken, and this hydrogen will be given off as proton. As you can see on your screens, the carbonyl carbon and the carbon, that which is the alpha carbon, it pulls the electrons towards itself, and the oxygen is pulling the electrons towards itself. Let us start from here. That oxygen, being more electronegative, pulls the electrons towards itself, as a result of which there is a negative charge on oxygen and a positive charge on carbonyl carbon. This positive charge on carbonyl carbon in turn pulls the sigma electrons between alpha carbon and the alpha hydrogen, which results in the double bond between the carbonyl carbon and the alpha carbon. and there is at the same time negative charge on oxygen. This oxygen picks up a proton, that is alpha hydrogen, or it picks up a proton from the solvent, resulting in the enolic form. In enolic form, the OH is directly attached to a double bond. Here I would like to clarify again or explain again the difference between the enolic form and the other form. In enol, other form of unsaturated alcohol. In enolic form, OH is attached to the carbon containing the double bond. So here you can see there is a dynamic equilibrium between the keto and the enol form of ethyl acetoacetate. The reason that we take this as a classical example, because it was the most extensively studied, it was one of the most extensively studied molecule. Reason being, ethyl acetoacetate was prepared by Geuther in 1863, and it was also prepared by Duppa and Frankland in 1865, and Geuther showed that the structure, the molecule which he had prepared was the enolic form. So he assigned it the enol structure and suggested the formula CH3C in bracket OH, that is this OH is attached to a carbon, then double bond between two carbons, H, COO, C2H5, which clearly indicates that this is a beta hydroxycrotonic acid. You know what is a crotonic acid? Crotonic acid is CH3CH double bond CH COOH. So it is an ester of crotonic ester, and the ester here is the ester of crotonic acid, and the OH group is present at the beta carbon, therefore beta hydroxycrotonic ester. In 1865, Frankland and Duppa also prepared acetoacetic ester by the action of sodium ethyl oxide on ethyl acetate. They showed that ethyl acetoacetate had ketonic structure and proposed the formula CH3CO CH2 COO C2H5. That is this molecule had a ketonic group, and they named it as beta keto butyric acid. Now, Geuther had assigned ethyl acetoacetate enol structure, whereas Frankland and Duppa assigned the same molecule the keto structure. So that means now both of them had to prove that the structures which they had proposed were correct. That is, they had to give evidences to support that the structure which they had given was correct. So two sets of reactions were proposed. One was in the evidence of the Geuther formula, that is, reaction supporting the enol form. So now Geuther had to prove three things. First, that the molecule has an hydroxyl group, molecule has a double bond, and then the OH is attached to the enolic form. That is, the OH is attached to the carbon containing the double bond. So first they proved that the molecule has an hydroxyl group. For this, they treated ethyl acetoacetate with sodium metal when sodium salt of ethyl acetate was formed and hydrogen was evolved. As you can see on your screens, reaction of enolic form of ethyl acetoacetate is shown with sodium. When sodium salt of ethyl acetoacetate is being formed, along with evolution of half mole of hydrogen, this clearly indicated that this molecule has a hydroxyl group in it. The second reaction in favor of hydroxyl group was where ethyl acetoacetate was treated with phosphorus pentachloride. When it was treated with phosphorus pentachloride, ethyl ester of beta chlorocrotonic acid was formed. This reaction again indicated the presence of hydroxyl group. You already know that alcoholic compounds react with phosphorus pentachloride or thionyl chloride to form chloroderivatives. So this clearly indicated that this molecule has a hydroxyl group. So as you can see on your screens here, again you can see the reaction of enolic form of ethyl acetoacetate with PCl5 when beta chlorocrotonic acid is being formed. Now they had to prove that this molecule has a double bond. So for this they carried out the reaction which we normally do for testing unsaturation in a molecule. Now what do I mean by saying unsaturation? That there is a double bond or a triple bond between two carbon atoms. Please remember, a carbonyl compound would not give this reaction because there is no unsaturation. There the double bond is between carbon and oxygen. So when the reaction was carried out with bromine, it was found that the color of bromine was discharged. The reaction was carried out with ethanolic bromine. So what kind of reaction is this? This is an addition reaction. As you can see on your screens, the enolic form of ethyl acetoacetate reacts with ethanolic bromine and a addition compound is formed where bromine is adding across the double bond. Now the next point, which is very important, they had to prove that the double bond and OH in this is existing as a enolic moiety. Now you know what is an enolic moiety. In enolic moiety you have a C double bond COH. See, if I like to clarify this further once more. Like if we have a grouping like CH2 double bond CHOH, then this is enolic. And on the other hand, if we have a grouping like CH2 double bond CH, single bond CH2OH, that is definitely not enolic. That is allylic grouping. In enolic grouping, you have to remember that OH has to be attached to an sp2 hybridized carbon. So for this what they did was, they did the test of ethyl acetoacetate with neutral FeCl3 when violet color was formed. And this is clearly indicative of phenolic compounds. So now they had proved that the molecule has hydroxyl group in it, it has a double bond in it, and it has enolic grouping in it. Now let us see what reactions did Frankland and Duppa put forward to prove that the molecule which they had prepared existed in the ketonic form. We know that the characteristic reactions of carbonyl compounds are nucleophilic addition reactions. So they carried out the reaction of ethyl acetoacetate with HCl and sodium bisulfite, which gave addition products and which clearly indicated that the molecule has a carbonyl group in it. As you can see on your screens, ethyl acetoacetate reacts with HCl to give an addition product where HCl is being added across the carbonyl group, resulting in the formation of cyanohydrin. And in second reaction, sodium bisulfite is adding across the carbonyl group, resulting in the formation of bisulfite. If we look into the mechanism of the reaction, which you can see on your screens, this is an example of nucleophilic addition. Because the carbonyl oxygen is more electronegative than carbon, it pulls the electrons towards itself, as a result of which the carbonyl carbon is electrophilic in nature. Now CN makes a bond with this carbonyl carbon, and H, that is as proton, makes a bond with the carbonyl oxygen, resulting in formation of cyanohydride. In the next reaction, which is again showing the mechanism of ethyl acetoacetate, the ketonic form with sodium bisulfite, you can see that proton is adding to oxygen and sodium sulfite is adding to electrophilic carbon of the carbonyl group, resulting in the bisulfite addition. The next two reactions again prove that the molecule has carbonyl group. In first reaction, ethyl acetoacetate forms an oxime with hydroxylamine. This is an example of a condensation reaction. As you can see on your screen, ethyl acetoacetate reacts with hydroxylamine, resulting in formation of oxime, and this is a condensation reaction because in this a water molecule is eliminated along with the addition compound that is being formed, and a double bond is created between the lone pair of electrons on nitrogen and the carbonyl carbon. In the second reaction, the keto form of ethyl acetoacetate reacts with phenylhydrazine to form phenylhydrazone. This reaction again clearly indicates that the molecule has a ketonic group in it. And as you can see on your screens, phenylhydrazine reacts with the keto form of ethyl acetoacetate, reacting in phenylhydrazone. So these two reactions clearly indicated that the molecule has a carbonyl group in it. Another reaction, which is a reduction reaction, which also proves now that the carbonyl group is the ketonic group. Because when reduction of ethyl acetoacetate is carried out with lithium aluminium hydride in pyridine or sodium borohydride, a secondary alcoholic group is formed, which clearly indicates the presence of the ketonic group. So as you can see on your screens, when the reduction reaction is carried out with lithium aluminium hydride in pyridine, or we can also use sodium borohydride, only the ketonic carbonyl group is reduced and we get beta hydroxybutyric ester. In this case, the reducing agents, being selective in nature, do not reduce the ester grouping. So this clearly indicates that the molecule has a carbonyl group, and the carbonyl group is ketonic group, since we are getting a secondary hydroxyl group here. Now the next point, ethyl acetoacetate on hydrolysis gives acetone. And we are carrying out the hydrolysis with dilute HCl or dilute NaOH. So when it is giving acetone, this clearly indicates that the methylene group present in ethyl acetoacetate is the reactive methylene group. Because when the hydrolysis is carried out, one of the hydrogen of water molecule adds to the methylene group, oxygen goes to the carbonyl group, and H goes to the ethoxy group, which you can see very clearly on your screens. And a bond is cleaved between the methylene group and the carbonyl group, resulting in the formation of acetone and carbon dioxide. At the same time, a bond is also being cleaved between the carbonyl and the ethoxy group, and this ethoxy group picks up a proton from a water molecule, resulting in formation of ethanol. So this, I have summarized this reaction in a very simple way. without going into the mechanism of the reaction as to how would you predict the products of the given reaction, that is the ketonic hydrolysis. And the second reaction, we find that ethyl acetoacetate also gives us mono and dialkyl derivatives. This again indicates that the methylene group which is present in it is active in nature, that is, it has an acidic hydrogen in it, because when the reaction is carried out with sodium ethyl oxide, as you can see on your screens, followed by reaction with alkyl iodide, monoalkyl derivative is formed. So this clearly indicates that the hydrogen of the methylene group is acidic in nature, because it reacts with a strong base, that is C2H5O-, resulting in the formation of carbon ion or the enolate ion, which then reacts with alkyl halide in nucleophilic substitution reaction, resulting in the formation of monoalkyl derivative. The mechanism of this reaction I shall be discussing in my subsequent lecture. Now, there was a lot of ambiguity, like which form of ethyl acetoacetate is correct, or how are they existing in dynamic equilibrium. This controversy on the structure of ethyl acetoacetate continued until 1911. KNORR in 1911 isolated both tautomers in pure form and demonstrated that they were readily interconvertible. And he proved that ethyl acetoacetate exists as a tautomeric mixture of the keto and the enol form, which you can see on your screens. That is, and he further said that the ketonic form will exist at say 92%, and the concentration of the enolic form would be 8%. Now, what do we mean by saying dynamic equilibrium? When I say dynamic equilibrium, it means that one form is continuously changing into the other form to maintain the percentage, that is the same percentage. Say for example, we add a reagent which reacts with the ketonic form. Then the entire system will behave as though it is made up of only ketonic form, because as soon as the ketonic form reacts with the reagent, the equilibrium will be disturbed, and more of the enolic form will be converted into keto form to establish or re-establish the equilibrium, that is 92% of the keto form and 8% of the enol form. And a similar procedure will take place when we add a reagent which reacts with the enolic form. Then whole of the system will behave as though it is made up only of the enol form. So KNORR, why did KNORR remove this controversy? Because KNORR in 1911 succeeded in isolating both forms. He cooled a solution of ethyl acetoacetate in light petrol at minus 78 degrees Celsius and obtained crystals which melted at minus 39 degrees Celsius. And this substance gave no coloration with neutral FeCl3. And it did not combine with ethanolic bromine. Therefore, it was the pure ketone form which corresponded to Frankland and Duppa formula, which you can see on your screens, the keto form. KNORR then suspended the sodium derivative of ethyl acetoacetate in light petrol at minus 78 degrees Celsius and treated the suspension with just enough HCl or acetic acid to decompose the sodium salt. He now obtained a product which did not crystallize but set to a glossy solid when cooled, and this substance gave an intense coloration with neutral FeCl3. Therefore, it was the pure enolic form corresponding to the Geuther formula, which you can again see on your screens. That is, we have shown you the enolic form in which the OH is attached to a double bond. Now, the thing that I want to remind you here, that generally we say the ketonic form is more stable. For example, if we take that of acetone, then we've seen that acetone in solution exists in ketonic form to 99.99%. That is, the enolic form is less than 1%. Whereas when we are talking of ethyl acetoacetate, here we find that 92% is the ketonic form and enolic form is a substantial amount, say 8%. See, when I say substantial amount, what I mean is substantial amount, 8 is substantial amount when compared to less than 1%. This is what we mean here. And why is it so? It is because, as you can see on your screens, that in ethyl acetoacetate, there is intramolecular hydrogen bonding between the hydroxyl group and the carbonyl group. And because of this intramolecular hydrogen bonding, this molecule is stable. And we've seen some other exceptions also, that the phenolic compounds, that is phenol, exists exclusively in enolic form since it is aromatic in nature. And we had also seen in one of the previous lectures that acetyl acetone also exists in the enolic form in small amount, because there it is existing because of the intramolecular hydrogen bonding, and second, the ring structure which is being formed there is 6-membered. And we know that 6-membered ring structures are stable. If you go back to cyclohexane, that is cycloalkanes, you know that cyclohexane is considered to be the most stable form of any cyclic compounds because it can exist in puckered form, where the bond angles and bond lengths are retained. So therefore, that molecule, that is acetyl acetone, is quite stable. So let me summarize as to what I have done in this lecture. I said that ethyl acetoacetate is an extensively studied molecule which is an example of keto-enol tautomerism. Reason being, it was prepared by Geuther, who said it is the enolic form. Then it was prepared by LiAIH and Frankland and Duppa, who said that this is the ketonic form. Then KNORR showed that it is in fact a dynamic mixture of ketonic and the enolic form. Last, we said that the enolic form of ethyl acetoacetate is stable because the molecule is stabilized by intramolecular hydrogen bonding. For this lecture, I had referred to the books of Carey, McMurray John, Wade, Nelson, Cox and Nelson and David and Cox, Finar and Morrison and Boyd. And I think you can also refer to books by Finar and Morrison and Boyd. Thank you.